Justin Miller, Rockstar College Physics here. What do we got going on? We got some more physics, of course. We want to start doing some work now. Not that we haven't been doing work previous to this, but there's more work to be done. And the work that we want to focus on is work done by a force. So, let us start with this. Just by writing this all down, work. Done by, oh my gosh, troubles writing letters already, by a force. Work done by a force. Well, if you go to work, you do some work, you get paid for work, you sit and do nothing, and maybe that's your work. But work in physics has a very specific definition. So what we want to do is define work. So let us just do this, right? So we're going to stick for now with just a constant force. Later on, perhaps we'll deal with some varying forces, but right now, let's just consider a constant force. Work done by a force, I'm going to put that is constant. We'll stick that there, and we're going to write this down. The work done by that force, so I'm just going to write it W sub F, so we can talk about a specific force, is equal to F hat dot delta R hat. That's the definition of work done by a constant force. We can even put 3 there and say, hey, that's what it's defined by. It's a force dotted into a displacement. Force vector dotted into a displacement vector. So before we really go on with this, what we got to note is, well, what is this really doing? What is this dot? You may say, well, that means multiply. And that kind of does, but it kind of doesn't. This is called a dot product. It's a vector operation. Dot operation. And of course, we have F hat as the force under consideration. Force being considered. Delta R hat is the displacement vector of the object on which the force F hat acts. So we got a force and a displacement vector. Dot product. Well, the dot product does something very specific, and what it does is it picks out mutually parallel components between two vectors and multiplies them together, forming a scalar quantity. So the dot product multiplies the mutually parallel components of two vectors together. And forms a scalar quantity. And in this case, the dot product between the force vector and the displacement vector gives a scalar quantity that we're going to call work, the work done by the force. All right, so let us see how this dot product works first, just in case you have not seen it, which is perfectly fine. So what we're going to do is consider two forces or two vectors. So let us look at the dot product. Looking at how the dot product works. Consider two vectors, A hat and B hat. So if I'm just going to draw two vectors out, I'm going to say we've got some vector A hat like that, and we've got some vector B hat like that. They're two different vectors, they have two different magnitudes, they point in two different directions. And what we want to note is, what is the dot product of A hat and B hat? So we want A hat dot B hat, and that's exactly how we say that. So what is this dot product? Well, as was stated there, the dot product takes the mutually parallel components of two vectors and multiplies them together. So what we got to figure out is either one of two things, either the component of B that is parallel to A, or the component of A that is parallel to B, and then multiply that component with the other vector. So let us consider this. We can write this as being equal then to A times B parallel to A. So if we take the magnitude of the vector A and multiply it by the magnitude of the vector B that's parallel to A, that will be what the dot product is. So let us look at this. So I'm going to take these two vectors and see if I can get some sort of representation of the parallel component of B with respect to A. So I'm just going to draw these again, but I'm going to draw them starting at the same spot. So we've got our vector A hat, and we've got our vector B hat here. And what we want to know is, hey, what is the parallel component of B with respect to A? Well, any vector can be resolved into two mutually perpendicular components with respect to whatever you want. So we're going to do that with B with respect to A. And what do we get out of this? Well, we get this. If I look at the projection of B onto A, this is what I get here. This is B parallel to A. This here would be B perpendicular to A. That's it. We resolve B into two mutually perpendicular components, the parallel and perpendicular component with respect to A in this case. So what we would have is the dot product between A hat and B hat is B parallel times the magnitude of A. That would be it. But we got to be able to extract out what is B parallel in this case. So what can we do with this? Well, we can identify that there has to be some angular separation between these two vectors. One points in one direction, one points in the other direction, so there's some angle theta that separates those two angles. Well, those two vectors. So how am I going to get this B parallel out of that? Well, what we can start doing is looking at some trig identities, right? The definition of the cosine of theta would be adjacent over hypotenuse, where the hypotenuse would be the magnitude of B itself. So I can take this and write that, well, the cosine of theta is going to be equal to B parallel divided by B. Where that B parallel is parallel with respect to A. So what do we get out of this? Well, we can write this then. B parallel is equal to B times the cosine of theta. So what does that allow us to do? Well, it allows us to write the dot product of A and B as, we can write it as A, then B parallel. B parallel is B cosine theta. A, B cosine theta. There we go. That's how we could represent the dot product between two vectors. The magnitude of those two vectors multiplied by the cosine of the angle between those two vectors. That's it. Well, that's one way to get this, but there's another way too, because it didn't say you have to do the parallel component of B with respect to A, or the last with respect to the first. You could do it the other way around as well. So we could also do something like this and say, well, this should also be equal to A parallel to B times the magnitude of B. So let's go ahead and look at figuring out what A parallel to B is. So we're going to take the same scenario right here. I'm going to draw these two vectors once again. Here's our A, and here's our B. Not quite, but try to make it look a little bit, at least in the same direction. Good enough. So what do we want? Well, we want the parallel component of A now with respect to B. So what we have to do is look at how we break this vector A up into two components. A component that is parallel and a component that is perpendicular to B. So this one would be A parallel to B. This one would be A perpendicular to B. And what do we have? There's still some angle that separates the vector B hat and A hat, which we call theta. This makes a 90-degree angle there. This maybe should be shifted down a tiny bit, but cheat this a little bit. Extend that out. And what do we get out of this? Well, if I want to know what A parallel is, I can again look at cosine. This is our right angle right here. So the cosine of theta is adjacent over hypotenuse, which would be A parallel to A parallel to B divided by A. So we go back with this. Again, we can write that the cosine of theta is equal to A parallel divided by A, which gives us that A parallel is A times the cosine of a theta, which gives us the ability then to rewrite this. We stick that in for A parallel, and we got A cosine theta times B, which is AB cosine theta. So the point with this is it doesn't matter which vector you're treating first, second, one parallel with respect to the other, or the parallel component of one with respect to the other. This is how we do it. You know what the two magnitudes of the vectors are, you know the angle that separates the two vectors. Finding the dot product between those two vectors is just that, AB cosine theta. So that's all the mathematical aspects of it. What do we have with respect to work then? Well, with respect to work, we can write then that work is equal to F delta R times the cosine of theta sub F. F delta R times the cosine of theta sub F. And the reason I put the subscript on that theta is so that we're reminded that we're looking at the angle between this force that we're considering the work for and the displacement that the object is undergoing. Because sometimes, hey, there's going to be multiple forces, and we want to be specific about which force we're looking at. So at any rate, F is the magnitude of F hat. Delta R is now the distance object moves. And theta sub F is the angle between F hat and delta R hat, the force vector and the displacement vector. So that's all great. This is what we get, strict definition. This kind of resolves out of it. So what we want to do now, other than be able to quantify work done, is kind of understand what the heck is work? Why do we care to quantify it, and why is it assembled like this? Why does it have to do with mutually parallel components? So what it comes down to is work is all about changing the state of an object. Changing the state of an object, which happens to be correlated with net force, right? A non-zero net force will change the state of an object. It will produce an acceleration. Well, if there is an overall amount of work done on an object, you basically get the same thing. You get that there's a change in the state of the object because, well, ultimately there's a correlation with an acceleration being produced and a change in velocity that then occurs. But it's a different way of looking at things. Different way of looking at things. So we can take something like a little for instance, right? Come over here. This, and I just want to get something so I can put something up on here. Got a little block here. Can put some mass in it, sure. It's a little block. It has mass with the mass, some total mass. And I can do stuff to it, right? I could come in with a force and start acting on it. And what do I do when I'm acting on it? I pushed it. Well, there was a force acting on it, and there was a displacement in the direction of that force. And And ultimately, there was a change in the object's motion, an acceleration that took place. All right, so a change in the state of the object due to a force doing work. My force did work. Well, what happens if I push on this object this way? I'm pushing on it right now, it's not moving. My force is doing no work because there's no displacement that's taking place. What happens if I push downward on this object? Well, still the object's not moving in this particular case, so the displacement would be 0, or the distance that moves would be 0, but we also have that the angle between f hat and delta r hat would be 90 degrees. Well, it's not really moving, so there is no angle there. The point is that a force may or may not be doing some work. And, well, the object may or may not be changing its motion. Ultimately, we're going to look a little bit deeper at this, what this correlates directly to, but it's all about forces imparting energy or extracting energy from a system. So this is where we start talking about energy considerations. So you say, well, we haven't talked about energy. Well, that's what we're going to do. So that's kind of where we're at this point. So what we want to do is take this concept of work and sort of unravel it and see what's inside, what sort of direct associations we can make with familiar material. So, yeah, let's do that, shall we? Yes, one moment. All right, so what we're going to do is do some work with this expression right here, so to say. Go ahead and throw that up there. Pull this on down here. And erase this stuff here. So again, we are considering a constant force here. Let us consider a constant net force to kind of see the overall aspect. Net force being just the sum of all forces acting. So let's look at the work done by the net force. Consider the work done by a net force sigma f hat. So what would we have there? Well, we would have that the work done by the net force is equal to the net force times the displacement multiplied by the cosine of the angle between the net force and the displacement. All right, well, let's just go ahead and assume for this that theta is going to be 0 degrees, that the net force acts in a particular direction, and that's the direction that the object undergoes a displacement. All right. Let us say that theta sub sigma f is equal to 0 degrees here. The force and the displacement are completely aligned with one another, which makes sense. Doesn't have to be the case, but it simplifies showing all this stuff. So now we've got this. We've got the work done by the net force is equal to that net force multiplied by the displacement. So what can we do with this? Well, we know some things, right? We know some things regarding what a net force does. We know that the net force produces the acceleration of the mass, right? So what happens if we stick that in right here? Now we've got the work done by the net force is equal to the mass times the acceleration times the displacement. All right. What else do we got going on? If the net force is constant, the acceleration is constant as well. Acceleration is also constant. And if the acceleration is constant, well, we know equation of motion for constant acceleration that allow us to determine that how fast, how far, what time, all the good stuff. So let's focus on this constant acceleration now. And there is a nice expression It says V final squared is equal to V initial squared plus 2A delta R. Constant acceleration, this is one-dimensional. This thing is moving in one direction. And this is it. Do you see anything familiar between these two expressions here? And hopefully you say, yeah, there's a common term. We've got an A delta R there, and we've got an A delta R there. So what happens if we go ahead and we solve this out for A delta R and then substitute it in there? Let's see. Well, we can write this as V final squared minus V initial squared divided by 2 is equal to A delta R. So I'm going to do that. A delta R is equal to V final squared minus V initial squared divided by 2 via this expression. Now we're going to take this A delta R and stick it in here. So now we can write the work done by the net force is equal to the mass multiplied by A delta R, which is V final squared minus V initial squared divided by 2. So I'm going to expand this out a little bit and write this. The work done by the net force is equal to, well, if I can factor out that 1/2 and then distribute that m over 2 through both terms, we can write it like this. 1/2 mv final squared minus 1/2 mv initial squared. That looks way different than what we started with, right? Looks way different than just f delta r cosine theta. Now we've got that the net work done, or excuse me, the work done by the net force is equal to this. What is this? Well, it seems to be a change in something, right? We have a 1/2 mv final squared and a 1/2 mv initial squared. The difference between a final state and an initial state. That's really about the velocity changing, right? If there is some net work done that's non-zero, these two terms have to be different. Well, we already know. That's what accelerations do. They change velocities. So if there is a non-zero net force, there will inevitably be some non-zero acceleration, which will change the velocity of the object. But notice that these aren't terms that are linear with respect to velocity. They go as velocity squared. We're going to define another quantity. Another quantity. Let us now define kinetic energy, which is energy of motion. Kinetic meaning motion, and energy, well, meaning energy. So what we have here is that these terms themselves represent a final kinetic energy and an initial kinetic energy. So we just define kinetic energy which I just generally use KE, so it's really easy to decipher. Hey, that's kinetic energy. Kinetic energy in general is 1/2 mv squared. That is the kinetic energy of an object. If the object is stationary, motionless, it has no energy of motion. The faster it goes, the more kinetic energy it has. What's that all about? Well, energy is about the ability to affect your surroundings, right? The ability to change the state of something else. I can have that there is some ball here stationary. It has no kinetic energy right now. But what can happen? Something can come along and strike it, exert a force on it, producing a displacement over some time interval of which that force acts, and impart some energy to that object. My hand comes, boom. Oh, that was kind of neat. Anyways, that is what we have. It's another way of thinking about forces and what they do. A non-zero net force changes the energy of the object on which it acts. Now, it can be imparting energy, increasing the object's energy, or it can be extracting energy, decreasing the object's kinetic energy, like in the case of friction. But ultimately, this is how we define kinetic energy, energy of motion. That's really, really important. And that's a really nice way of looking at things in terms of something that is a scalar quantity now. Energy is a scalar. It has no direction. It's just a how much. How much energy? So let us go a little bit further with this. Kind of see a couple other little things with this. And then we'll move on. So what we have with this at this point is from this right here. I'll write it down again. So we have the work done by the net force is equal to 1/2 mv final squared minus 1/2 mv initial squared. Well, we can call this the final kinetic energy and this the initial kinetic energy. So we can write this as the work done by the net force is KE final minus KE initial. And what can we do with that? Ultimately, we can say that the work done by the net force produces the change in the object's kinetic energy. This is known as the work energy theorem. Work done by the net force, or by a net force, produces the object's change in kinetic energy. That's it. That's what work done by the net force does. You can also say, hey, the net force produces the object's acceleration. That's great, but this again, another way of looking at it. The net work done produces the object's change in kinetic energy. So that's why we care to define work, because from it we extract the idea of energy of motion and changing, once again, the state of an object. And energy considerations end up being very, very important in physics, and much more preferable to lots of this vector stuff because it's a scalar quantity. So let's look at the units. SI units of work. Well, we've got the units of work have to be equivalent to the units of force times displacement, right? So we got force times displacement. Cosine of theta has no units, not worried about that. So this is going to be newtons times meters. Newton meters, Newton meters. Well, we also have, from what we have up here, that work done has to have the same units as kinetic energy. Change in kinetic energy and kinetic energy have the same units, right? So what do we have for the units of kinetic energy? We have kinetic energy as 1/2 mv squared. So we can put that 1/2 mv squared. Well, that is going to be equal to kilogram meter squared per second squared. Kilogram meter squared per second squared. So at a glance, you may say, oh, those are two different things. We've got to remember what a newton is, right? A newton is a kilogram meter per second squared. Kilogram, one of the meters per second squared. There's the newtons, there's the other meters. These two are the same unitizations, as they should be, because they're equivalent, right? So what do we get out of this? We call the unit Newton meters. It's not that we call it. 1 Newton meter is equal to 1 joule. Use capital J for. The joule is the SI unit of energy. Joules happens to be the same unitization as work, and kinetic energy, but it overall is the SI unit of energy itself. There's different types of energy. This is just one, kinetic energy. But that's what we've got going on. So we quantify work done or kinetic energy in some number of joules, and note that it's just a scalar quantity. No vector direction to it, even though it's associated back with a force vector and a displacement vector. So the idea, once again, with work is that it's only a force that is in the direction of the displacement which can be responsible for producing changes in the object's energy or changes in the object's motion. If I take an object here and I push on it this way and it moves up, that's not this force pushing it that way that is responsible for it going up, right? Something else has to be responsible for it. So if I'm pushing on something but it goes up, well, this force here is doing no work because there's no displacement of this object in the direction of that force. That's why we have that dot product. If you push on something one way and it goes perpendicular to the direction you're pushing, then guess what? You're pushing for nothing because you're not affecting its motion unless it's being redirected with pulley systems and all sorts of stuff like that. That's different. Anyways, that's the idea with work, and we've got all sorts of things that do work. Any force that acts in or aligned with the direction of motion of an object is doing some amount of work. Could be positive, could be negative, and that's stuff that we'll look at here.